Again, there is some echo. Again, I'm Zoltán Lehóczky, and with my colleague Benedek, we'll talk about what's behind this horrific long title. We are from Lombiq Technologies, as we have already heard. We are also the sponsors of this year's conference. And day to day, we are a software development company. We work with Microsoft technologies, and we mainly do web development services. We have clients mostly from North America, and actually the Smithsonian Institution, the biggest museum complex in the world, and Microsoft itself is also our customer. Although in day-to-day, we do these. When the night falls, we have research and development projects like Hastlayer. Now, this is something that we also collaborate on with Wigner. So, as also said, since last year we have a partnership, we have engaged into a partnership with Wigner, with which we also try to further science with our own means. Without going into details of what Hastlayer itself is, disclaimer first. Please note that Hastlayer currently is not a mature product yet, is in the alpha stage. Now, here are a few people who also were there last year on the GPU Day conference. I said experimental then, so you can see the immense progress. Now it's in alpha stage, not experimental anymore. So what is Hastlayer? In a nutshell, what it does is that it's an automatic tool that takes logic expressed as software and converts it automatically into logic expressed as hardware. And it does it with FPGAs. Yesterday we have heard a pretty in-depth introduction of FPGAs from Sulaiman. So just in one sentence, FPGAs are computer chips that, within limits of course, can behave like any other computer chip. Now we utilize this with Hastlayer. We reconfigure FPGAs to have, well, application-specific integrated circuits in the end. To be a bit more precise, Hastlayer actually processes .NET software written from the .NET platform, creates VHDL code, which is a hardware description language, and outputs FPGA logic in the end. Now the advantage of .NET, if you are not familiar with it, is that all .NET languages compile into the same bytecode. So that's good because Hastlayer can process assemblies or software written in a variety of languages, including C#, of course, but also functional languages like F#, or C++, or even scripting languages like Python, or even JavaScript or PHP. But why on earth we do this? Well, first of all, FPGAs allow massively parallel execution. So for certain applications where parallelization is available and computations are mostly done with integers, FPGAs can provide a significant performance increase. And not just that, but since they are low-power devices running on slow clock cycles, on slow clocks, the power consumption can be lowered as well. And with Hastlayer, all of this is still like writing software, because we have the automatic tool to convert your software into hardware. No FPGA design, no hardware engineering knowledge required. So let's see a short demo of how all of this works. I'm now opening Visual Studio, which is the development environment .NET developers commonly use, but this is just an example, you don't need to use that. We have a very simple, synthetic example application here that I will use Hastlayer to accelerate. The logic, what it does is as following. By the way, who has ever written some program code here? Okay, so almost everybody, that's great. For those of the few guys here who haven't, bear with me, it will be simple enough. Basically what we have in the core of the algorithm is some very simple decision logic. So it does something if the input is something and something else if the input is something else. So this is the decision logic, and it will do this many times after each other. That's it basically. And not just that, but we will do this little logic many times in parallel. By utilizing standard .NET parallelization constructs, in this case the task parallel library, we will start, in this case, 200 threads on the CPU. So what you see here is a very simple parallel .NET program. And it's, by the way, written in standard C#. So nothing Hastlayer specific is here. Obviously, there are limitations in what you can do with Hastlayer, and naturally, it doesn't always make sense to transform something into hardware, even if it's possible. But there is very little to learn. If you're a software developer, you will probably need half an hour to get going with Hastlayer. And there is only a single piece of API that you need to learn about Hastlayer, which is this simple memory object, which is basically a simplified memory management memory management API, so to say, but not much to it. And how you will execute this program that's inside this run method is as following, like this. So exactly nothing special. You just call that method and it will run it. Now, what we have in this console application I'm showing you the code of is that there is some configuration and Hastlayer, but in the end, that piece that will be transformed into hardware is still run seemingly as simple software. So all the communication that happens with the FPGA board is abstracted away. You just write standard-looking .NET code. You just call standard-looking methods, and in the background, the FPGA execution will happen. I have already programmed the FPGA, and I already have the shell that handles the communication and memory management on the FPGA side running. So I'm now just starting this program here to see what happens. What happens now in the background is that the hardware description will be generated, and once that's done, there will be a communication handshake with the FPGA, and then the execution actually happens. And it's indeed happened now. What we see here are some results. There were 3 method calls. You see that on the hardware it took 300 milliseconds each time. Since it's hardware, if the runtime or if the number of steps your algorithm has to do doesn't depend on the input, then it will be always constant because there is no operating system, no noisy neighbors, no other applications running at the same time. And altogether, with the very slow serial communication I have here, it took around 400 milliseconds with the round trip. Compared to that, on the CPU, on this laptop, it took, well, around 10 times that much, around 3 seconds. Now, obviously, this is not a scientifically accurate measurement, but this can give you an idea that if you have some massively parallel application, what kind of performance increases are possible. So, that being said, let's go back to the presentation. Oops. I should have pushed Shift F5. Now, we have seen, we have previously put coprocessor into the title because we have utilized FPGAs as kind of coprocessors working for a standard application. But now also let's put science into the scientific coprocessor. There is something called the 3D KPZ surface growth simulation. I won't go into detail on this, well, mostly because I don't fully understand it. But what this thing is about is that it's an algorithm to simulate the surface smoothness of some material. It can simulate the propagation of imperfections on the surface, which is, for example, useful if you have a semiconductor wafer. So this is directly applicable in the semiconductor industry. If you want to know about the science behind this, and this is a technical talk, so I won't talk about the science here. If you want to know about the science, please refer to the talk of Geza Odor from last year's GPU Day. He talked about that in detail, as well as the GPU implementation of the algorithm. Or ask the Wigner guys, because they know it. They told us how to implement it. But let's see how it works in Hastlayer. I will now go back to Visual Studio and change which application to run. This will be a graphical application. So let's see how it looks like. Not much here. Basically, the main input of the algorithm is the iteration count. This is an iterative algorithm, so the iteration count will tell it how many iterations to execute. Let's see what happens if I just run the simple version of it. You see that here below we have a graph that shows how the smoothness of the surface is. It hovers around this line, which will be the perfectly smooth version. But this is random, so we expect some variation around it. Now let's try all this, the same application that would go onto the FPGA, the same algorithm. Let's try it on the host PC, because what I've shown you before was the graphically using version of it, so that's a bit different. So let's see what happens now. It is done. It finished, so we can access the results in the background, even programmatically, and it finished in roughly 1.5 seconds. So far, so good. Now let's see how it works with Hastlayer. And for this, I will need to change the program that's running on the FPGA, but I will need to change the hardware configuration of the FPGA to have this other application-specific hardware core. So now I'm reprogramming the FPGA and starting it again. So that's just a few seconds. Eventually, we will also automate this, but for now, you have to click through it. And now while this is starting on the FPGA, let's start our program again. This time, I will run the same thing that I've run previously, but it will happen on the FPGA. So it's still loading. Sometimes it takes a bit more time. Actually, what we have on the FPGA side is well, a hardware framework and also a bit of software. The hardware framework is kind of the whole shell around that custom logic that we generate. We plug this custom logic into this hardware shell. That hardware shell deals with memory management, accessing the peripherals like the serial port or the Ethernet port, because we support that as well. And it also has a software processor on it that runs a program to handle everything that's unsuitable for hardware. And now it's started, so let's get back to our program and let's see the Hastlayer accelerated version. Remember, it took around 1.5 seconds to run on the CPU. And now it runs on the FPGA. We have to wait a bit for the result, and it's done. And now the execution time is 5 seconds. So you could tell, okay, Zoltán, this is pretty embarrassing. This is deceleration, not acceleration. And you are right. Well, first thing, this application is a work in progress, so currently it's just sequential. What I told you before is that it really only makes sense to use FPGAs if your algorithm is parallelizable. This doesn't use any of that. However, what this deceleration still shows is the potential that you can still get. Because this FPGA I have here runs on 100 MHz. The CPU in this laptop runs on 2.2 GHz, so 22 times higher clock frequency. And still the FPGA implementation is just roughly 3 times slower. So the FPGA implementation is much more efficient per clock cycle. And that also means that probably per power consumption as well, but we haven't made measurements here for that. So that's about KPZ. Again, please ask the Wigner guys for any more details on that. And we will continue with something groundbreaking. I say that because this is not something we have come up. And my colleague Benedek will talk about that. So come on back.
Thank you. Hi, everyone. Thanks for the introduction. So what I would like to talk to you about is hopefully revolutionary number format, which is called the UNUM, the Universal Number, which was developed by a gentleman called John Gustafson. He's an American computer scientist who's also, by the way, done a lot of research in HPC and a lot of work in that field as well. And he's the author of the End of Error book, which is basically a very nice a story-like description of how the universal number was developed. It basically describes the science and reason why it was developed and how it was developed, and contains a lot of nice examples and pseudocode. So if you want to check it out, if you want to actually look into the universal numbers, make sure to check this book out. You can, I don't know, buy it on Amazon, for example. So why bother creating a new number format? So the IEEE standards have a fixed layout. These fixed layouts were basically established decades ago, where when computation was radically different, our computers were much slower, million times slower, perhaps. And yeah, if you have a different kind of problem that didn't exist decades ago, you may want to radically change your approach as well. And we also have hardware restrictions. So as computer science evolved, basically all the science that comes along with it, how you store, how you process numbers, need to be evolved as well. And the universal number is a huge leap in that kind of evolution as well. The IEEE standards have a lot of wasted bits. So even if you have a processor that very efficiently calculates with a certain type of number, even in that case, you actually waste some of the number space that you could use. That's because, for example, the floating point standards have multiple millions of different kind of NATO number declarations that basically do nothing. The idea behind that is that there's the quiet NATO number, which is an error, but I can still continue execution, and the signaling NATO number is an error where you need to stop execution because something really bad happened. And basically this is the only two that makes sense now, or what we use now. But back in the days, the idea was that we will have more kind of errors, but it didn't happen, so we just wasted a lot of space. And like I said, decades ago, people even if they were really they had revolutionary ideas, they had really good imagination, they couldn't really think about all the problems that we have right now. So these number formats are really baked in, and sometimes they don't really accommodate the precision we need. So the universal number is the superset of the IEEE 754 standard, which is the floating point number standard. You can think about it, basically the floating point number is an extension of the integer, and the universal number is an extension of the floating point number. Universal number was implemented in several languages so far. You can get it in MATLAB, Mathematica, Julia, and C. And we are working on the .NET implementation. This is also part of our collaboration with the Wigner Research Institute, so they actually suggested that we should try this. And the other reason behind it is that floating point calculation on FPGA is really expensive, so it takes a lot of space of your chip. Also, if you don't want to develop it for yourself, you need to purchase it, which is also expensive. But hopefully the universal number can actually substitute this kind of investment. So how does it work? Why it's better? So universal numbers allow you to define your own number layout. So that's why they are universal, because this is not baked in. The number actually describes itself, how the layout is created. And just like that, we are honest about the fact that some of our algorithms are not as fast as they should be currently on an FPGA. The universal number is honest about random mistakes. So if you have a certain precision and you give like a half precision floating point number, a specific number that doesn't fit into the precision, that is going to lie to you when you ask the number back. It's going to say that this is a certain number, but it's actually not, because there's a rounding error. So the universal number actually tells you when there's a rounding. And a very nice feature of the, I think the MATLAB or the mathematical version is when you are actually computing something, you can tell it to stop execution when there will be a rounding error, and it will tell you if you need to increase your precision and how much you need to increase your precision, which is really cool. So like I said, there's no rounding or over or underflow. So if there will be an overflow, it will just tell you that it's too much for me to describe this number, and here's how to change it for you to be able to actually represent the correct number. And it doesn't waste a number space like the floating point standards. So you really have all the combinations of the bits inside the number have an actual meaning, not like the standards. So if we compare. Yesterday there was some talk about the half precision floating point number in terms of machine learning and maybe some other algorithms. So it came up regarding GPUs. So that's why I'm using this for a comparison. It obviously has a sign bit, 5 bits for the exponent, and 10 for the fraction bits, plus 1 for the implicit bit. So the universal number doesn't have these fixed numbers, but the layout is very similar. So you also have the sign bit. You also have exponent bits and fraction bits with an implicit bit, but their size is actually described by some additional metadata, which is called the U tag, the unum tag. And the unum tag actually consists of 3 other parts, which are kind of similar to the original 3 parts that you have in a floating point standard. One of those is the uncertainty bit. So this is where the unum actually tells you that there's a rounding error, and this is really useful because you actually get an honest answer. You may not get a precise answer, but you will be able to tell whether you need to do something about increasing your precision. So the last 2 parts is actually describes the size of the exponent and the size of the fraction. So E size is just a string of bits, where the bit actually represents the size of E size, which is the exponent bits, the number of exponent bits, and the same goes for F size. So it's really just basically copying the original floating point format, creating some additional metadata with it, but also the last 2 parts in the metadata represent the size of the original part. So that's why it's so flexible. So the way you can initialize a universal number is you can tell that I need this configuration. So let's say I need 20 bits for the fraction and maybe 5 for the exponent. And from that you can actually calculate what kind of what the U tag should look like, because the 2 to the power of the exponent size, so that describes the size, the number of bits in the exponent, is actually the E size. So there's a direct translation between the 2, or you can just define the environment. So the environment is the actual technical term used by the author, where you say that the number of bits that describe the exponent and the number of bits should be, and the number of bits that describe the size of the fraction is going to be this number. So that's why it's flexible. You can always change those, and your number format is going to be just yours and specific to your problem. So the other benefit, like I said, since it's not wasting number space, it needs less bits, fewer bits to describe the same information, which is really useful if you want to, if you need to lower your computational needs. You can optimize it for integers, of course. So that's why it's called universal, because you don't necessarily need to compute floating point numbers. You can calculate with integers if you want. And if you want to describe ridiculously big numbers, you can always do that if you don't need precision. So you can actually sacrifice precision for high dynamic range if you want to do that. So this really shows the flexibility. And like I said, if you have a specific problem, if you are able to determine what kind of range and what kind of precision you need, you can tailor your own number format to that specific purpose. You can even bake it into an FPGA if we will, as soon as we implement it. And like I said, the mathematical demo is really awesome in a way that if you have some kind of error in terms of you have less precision that you would need based on the computation, it will just tell you and you can reconfigure it and rerun it. And since we have the U-bit, the uncertainty bit at the beginning of the metadata, you can actually determine that, or you can actually see that basically the universal number space consists of points and ranges. So when the U-bit is 0, which means that yes, I have an exact answer within this precision, then that's a point. But the same universal number where the U-bit is 1 is actually an interval. So basically, it's the interval between the exact universal number and the next exact universal number. So you can actually cover the whole real number space with it. As for the future, or what to try as well, this is just a very simple high-level overview of the concept. There's another notion called the U-box, which is the multi-dimensional universal number. The Union 1.0 concept also contains the U-bound, which is similarly to the UNUM being a superset of the floating point format. The U-bound is a superset of the IEEE 1788 standard for interval arithmetics, and a new generation of the universal number called the UNUM 2.0 is in development or almost finished as a concept. It's really nice because there's a lot less edge cases. So implementing the universal number in .NET is really a challenge, especially that we have to consider that we are going to run it on an FPGA, so we need to create a lot of fail-safes, and yeah, the number of edge cases is really huge. So actually, since we weren't able to actually properly translate it to an FPGA, we were debugging it at midnight still, just before the presentation. Yeah, well, that's how it works. If you are on the cutting edge, then yeah, sacrifices need to be made. But what I can show you is how it works on the CPU. So we really actually wanted to show you how it works on FPGA, and it will happen. It will happen very soon. We are making really good progress. What I'm going to show you here is not this one, but maybe, oh yeah, this one. So this is a very simple algorithm that actually sums the powers of 2. So in terms of computational precision, summing the powers of 2 is not a big deal, but it's a simple demo that shows you that you can work with ridiculously huge numbers. As soon as we have the proper implementations for all the operators and all the little tidbits that needs to be implemented for it to work with real floating point numbers, we will have really awesome results. But if I run this program, it will actually sum all the powers of 2 until 255. So yeah, it really nicely gradually spits out all the results. I also wanted to show you that the environment we're using here is a 4/8 environment, which means that the number of bits in the fraction can be 2 to the power of 8, and the number of bits in the exponent can be 2 to the power of 4. So that's what the 4/8 environment means. As for comparison, the 3/4 environment is kind of a very simple way to start. It is 33 bits long. If you are using all the bits that you need in that environment, you can actually sacrifice 1 bit of the fraction, for example. So that will be only 30, so that will actually fit into 32 bits, which is really nice. So this is really annoying that it's 33, but yeah, it's mathematics, you can't change it. But yeah, so this is a very simple general overview of the concept. I hope it's caught your attention. I think it's something to keep an eye on because, you know, all of you are, and everybody in the scientific field working different kind of problems, and if you need specific precision, for example, or a specific kind of number space for your problem, you can actually save a lot of space or a lot of computation if you optimize a number format for your specific problem. And I think that's it for universal numbers. If you have any questions, you can just ask in the Q&A session or find the red shirt guys. And yeah, that's it. I think we can continue with the closing.
Are you able to make this code as FPGA bits too?
Sorry?
Are you able to make this code as the FPGA bits too? To run this code as the FPGA bits too?
The universal number?
Yes.
Yeah, that's the aim. So right now we are only running it on the CPU,
Okay.
but we are actually in the process of optimizing the code a little bit, because it's some of the, so you know, like Zoltán mentioned, we are working with Microsoft.NET and we are writing code in C#, which is very high level language, and it's really comfortable. We really love it in our everyday, you know, life as a web developer. But if you have to reach down to the hardware, sometimes, yeah, there's a lot of sacrifices. So we need to lower our expectations in terms of, you know, how comfortable it is to write code. So right now it's running on the CPU, and it will run on the FPGA fairly soon, I would say.
Do you want?
It's on.
Okay. Do you want, for example, some high-level synthesis tools using data? Do you want to make synthesis of the FPGA just from C?
So what we are doing basically is we have the C# implementation for the universal number, and we are actually going to use Hastlayer to be able to synthesize it into to the FPGA. So basically, so on one hand, the universal number is a really nice concept, and as soon as we actually have a working prototype, or everything is working in terms of operators and all the different number formats, we can accommodate the standard number formats. We will have an open source. We will open source it, so we will have a C# implementation of the universal number, which is really cool because there are tens of millions of .NET developers in the world who could actually use it, even if they are only using their CPU for computations. But then there's also another aspect of the fact that floating point calculations on FPGA are quite expensive for two reasons. So the universal number is a substitution for that. So what we hope to achieve is that we don't have to use a standard floating point format on an FPGA because it takes a lot of space. We might be able to simplify the UNAM concept and distill it in a way that it's efficient on an FPGA, and hopefully more efficient if you have a specific problem.
But then all the special math functions you would also have to implement in an efficient way.
Yes,
that's
it's
in general not possible, right? In some sense, you have to have favorite combinations of these two numbers, of the two sizes, and maybe for those specifically have tuned functions. Yeah. But to have an assembly essentially generated in the CPU side efficiently for arbitrary numbers, that's really tricky.
Yeah, yes, it's tricky implementing these. So what we have right now is basically we can add integers and subtract integers, and that took weeks. So it's, the number of edge cases is like insane, and actually the fact that we are actually working with the universal number is really good for Hastlayer. So we also discovered a lot of problems or issues to fix with Hastlayer. So it's Zoltán actually said, and I'm quoting him from yesterday, that universal numbers are the perfect hallway testing for Hastlayer, because you know every kind of problems come up, and you know we just we can fix them, but there's a lot of them. So actually one of the ideas behind the universal number is that you don't really run away from the standards, from the IEEE standards, but you find the environments that are close to those standards and stick to them. And if you stick to those standards, even with the universal number, you will be able to reach higher precision. But you will also have kind of the benefit that the number of bits that describe your number are really close to the powers of 2 that we are very used to.
Sorry, can I also reply to that? Just let me also reply a bit for that, to that. It's okay. And by the way, that was.
Oh yeah, sorry.
So you don't exactly have to tune tune Unum for your favorite combination, as you said, because the Unum environment is configurable. So you can use your own Unum configuration, even multiple ones in the same application.
Well, that's so fine. If I want to say X Unum evaluated it most efficiently on the particular hardware, exponential, I just learned a couple months ago from these guys here that actually even the exponential is done now totally via normal multiplication and various other operations on the SSE side of the CPU, because it's, and maybe like 1,000 such operations, because that's faster than to do the old exponential on the IS387 or whatever part is now called. And so these are all very complicated things in practice, and they are fine-tuned to that particular precision that you need to have. So in principle, probably this is solvable, but in practice it will boil down to somebody has to convert some favorite combinations of numbers and write the addition codes in it, so finally when I run my math, I can run it quickly.
Yeah, that's right if you don't have application-specific hardware, but with Hastlayer you will have. So that's, again, something we can kind of bridge.
So you mean you will have a general exponential calculator, and somehow this will run optimally on your FPGA somehow, with arbitrary number of bits that I want in my numbers?
You can, but you will be able to specify the optimal Unum environment size for that. So, well, within Hastlayer and FPGA limits, of course, and within the limits of our implementation.
I also feel that an algorithm which runs with those particular sizes, which runs the most efficiently with those particular sizes.
Not really. So the good thing about the universal number is that the algorithms are basically the same as for all the environments. So you don't really need to care about that. You have to implement them once, and it will work for all environments. Of course, you can optimize for if you have a specific precision that you want to use. You can probably try to optimize for that, and we actually try to do that. It's really hard on an FPGA, so I wouldn't really say that it will be feasible on an FPGA, because the actual algorithms and the space it takes up on your FPGA will be just huge, and you won't be able to use as many different computing cores on your FPGA, because the universal number and all the algorithms itself is going to take up a lot of space. So I would say that it's well, you need to define an environment that suits your problem, and you may want to try to optimize, but not necessarily because it's optimized in itself. So it will work nicely, but you can try to optimize for edge cases, for special cases.
I'm very skeptical. I mean, even divisions on 64-bit are parts of it in tables, parts of it in loops, parts of it in whatever, and they are all optimized to do click divisions in 64 bits.
Yeah.
There's all these other tools in there, not just the...
Let's pick this up with Dr. Gustafsson in the library.
Yeah, I'm very curious about
this. He is probably better suited to answer these kind of questions.
Yeah, but actually, as a side note, so another colleague who is working with us on the Unum implementation said that probably multiplication and division will be easier to implement than addition and subtraction. So I'm really hoping that will happen, because addition and subtraction was really painful, even for integers. And we are working on actual floating point numbers now.
Okay, so if there isn't any more questions, or is there any? Okay.
So Actually, I have a question for both of you. So my first question is whether you consider implementing Hastlayer based on other intermediate representations, for example, LLVM-IR, because that would make it accessible to even more developers who are not using .NET-specific technologies. And my other question is, are the parameters of the universal number dynamically adjustable? Because I could imagine, for example, a relative differential equation solver when it could lower the precision dynamically as it for better performance, but increase the precision for more precision as necessary.
Let me answer the first question. No.
Oh, sorry, let me answer the second question. Yes.
Thank you.
In a bit more longer version, as to LLVM, processing .NET bytecode is complicated enough. I think where the .NET and LLVM worlds meet is, I can't remember the project's name, but which basically makes the .NET bytecode compatible with LLVM. So to be compatible with LLVM ourselves, we would need to process LLVM bytecode, which would be something completely different. For now, just .NET bytecode is in the scope.
Yeah, actually, let me expand on the answer. So the answer is still yes, but so there's always a but. On hardware, so we are obviously, first of all, we care about FPGAs and Hastlayer and stuff like that, but we also care about the fact that the unit should be usable on CPU. So yeah, we are .NET developers and we like the other .NET developers. So if we can create a nice implementation for CPU, then we will do that as well because it's really cool. So on the CPU, you can change dynamically your environment, but on the FPGA, it's not really feasible because everything is baked in. So you are creating hardware, and on the fly configuration is not really feasible. What you can do is that if you can sacrifice memory for the sake of increasing the number of bits that needed for a number, then you can actually change within that limitation, but not you can't really go over it because it's hardware.
But it has to be in compile time.
Yeah.
Okay. So if you have any more questions, we can continue in the lunch break. So thanks again for both of our speakers.
Thank you.